this module, we'll start our discussion of semiconductor devices, and we'll begin by discussing semiconductor diodes. Semiconductor devices are so important nowadays that you can find them in almost every electronic devices. So that makes them important and interesting to study in this course. So what are semiconductors? As the name implies, they are a class of elements having a conductivity between a good conductor and that of an insulator. There are three commonly used semiconductors, and these are the germanium element, silicon, and the compound gallium arsenide. Germanium and silicon are single crystal materials having a repetitive crystal structure, while gallium arsenide, along with other compounds like cadmium sulfide, gallium nitride, and gallium arsenide phosphide, are constructed with two or more semiconductor materials of different atomic structure. Um, the building blocks of semiconductor devices are made up of what is called the N-type and P-type materials. These materials are created using or by doping semiconductor materials with impurities. The purpose of doping the semiconductor material is to change the characteristics of that material. Now, an N-type material is created if a semiconductor material is doped with a pentavalent material. So a pentavalent material is a material that has 5 valence electrons. So these are the electrons outside the orbit of the atom of that material. An example of these materials are antimony, arsenic, and phosphorus. On the other hand, a P-type material is created if it is doped by a trivalent material. So a material having 3 valence electrons, such as boron, gallium, and indium. So what are semiconductor diodes? So these are two-terminal semiconductor components that conducts current in one direction. Um, so it has a very low resistance in one direction and a very high resistance on the other direction. So these are uh, actual pictures of semiconductor diodes. Now they are constructed by joining the N-type material and the P-type material. The P-type material, or the terminal that connects to the P-type material, we call it the anode, while the terminal that connects to the N-type material is called the cathode. This is the symbol of a diode. So it looks like an arrow with a vertical line on the pointed side of that arrow. And this is the actual picture of an actual diode. So the terminal near the band of this diode is the cathode terminal. So that makes the other terminal the anode. We also have the picture of a vacuum tube diode just for comparison purposes. So prior to the invention of diodes, we use vacuum tube diodes. So these are very large devices compared to um, semiconductor diodes, and they consume a lot of power. There are two conditions operationally for a diode, and these are the forward bias and reverse bias conditions. So when an anode terminal of a diode is or has a higher potential than the cathode, means it is more positive than the cathode. That diode is said to be forward biased. Now for silicon diodes, the anode terminal must be at least zero point 0.7 volts above the cathode terminal, while for germanium-based diodes, it must be at least zero point 0.3 volts for the diode to be in the forward bias condition. A diode that is forward biased has a very low resistance, and sometimes that resistance can be ignored. When the anode terminal of the diode has a lower potential than the cathode, that diode is said to be in reverse bias condition. A reverse bias diode has a very high resistance, and no current can almost no current can pass through that diode in reverse bias condition. In the analysis of circuits involving diodes, it is sometimes convenient to replace the actual diode, with an equivalent circuit for that diode. There are uh, three categories of equivalent circuits of a diode. These are the piecewise equivalent circuit, the simplified equivalent circuit, or simply the ideal equivalent of the actual diode. In this module, we'll be talking of the simplified equivalent circuit of a diode. So when a diode is in a forward bias condition under DC, that means it is um, connected to a DC source. The actual diode has a voltage drop equals to its turn-on voltage at any level of diode current. This means that in a forward bias condition, that diode can be replaced by a voltage source that is equal to its turn-on voltage in series with an ideal diode. So the actual diode can be replaced by these two elements. So the voltage source having a voltage equals to the turn-on voltage V sub k in series with an ideal diode. For silicon, we have turn-on voltage of 0.7 volts, and for germanium, zero point 0.3 volts. Now, an ideal diode is simply a diode that is a short circuit when forward biased and an open circuit when reverse biased. A diode can either be in the on state or in the off state. If a diode is in the on state, that means it is in forward bias condition, and that the voltage across it, the voltage V sub D, is greater than its turn-on voltage V sub k. If a diode is off, that means that diode is in the reverse bias condition, and that means that the anode potential is less than the cathode potential. If the voltage across the diode V sub D is between 0 and its turn-on voltage, that diode isn't considered forward biased or reverse biased, but it is in the off state. Therefore, if V sub D is less than the turn-on voltage, the diode will always be off. Take note that the voltage across the diode V sub D is always taken as having a polarity that is positive at the anode, while it is negative at the cathode terminal. Now, in the analysis of circuits involving diodes, it is always necessary to first determine what is the state of the diode. Um, so the state of the diode can be determined by first taking out the diode from the circuit and then computing the voltage across that open terminals where the positive polarity corresponds to the anode terminal of the diode that was taken out of the circuit. If the open circuit voltage is greater than the turn-on voltage of the diode, then that diode will turn on. Otherwise, it will not turn on. If the diode turns on, that means that it can be replaced by a simplified equivalent circuit. So let's have a simple example here. So we have a resistance uh, that is 1 kilo ohm connected to a 10 volt source via a diode. So the diode is a silicon, so therefore it has turn-on voltage of 0.7 volts. So we're required to determine the voltage across the diode, V sub D, the current through the circuit, and the voltage across the resistance. So first we need to identify whether the diode is in the forward bias condition or reverse bias. So one of the ways of uh, determining this is by taking out the or removing the diode first from the circuit. So let's remove it. Um, okay, so remove that diode. So this is 10 volts and this is 1 kilo ohms. Now, so we would like to know the voltage across these open terminals. So let's label this plus corresponding to the anode of the diode, and this is minus. Now to get VOC, we can do a KVL around the loop. So since this is an open circuit, meaning there's no current, so current here is 0 amperes. So if you're going to compute for VOC, that will give us positive 10 volts, meaning this voltage or this diode will go into forward bias condition since VOC is greater than its turn-on voltage of zero point 0.7 volts. So therefore we can replace this circuit by, or we can replace the diode by a zero point 0.7 volts source that is in series with an ideal diode. And since we are talking about ideal diode, and this diode is in forward bias, that means I can replace the ideal diode with a short circuit, and that should further simplify the circuit as something like this. So from here we can perform another KVL so that we can solve for I. So that would be minus 10 plus 0.7 plus um, 1000 I equals to 0, and that should give us um, 9.3 milliamps. Okay, so we can compute for V sub R by Ohm's law, and that is 1000 I, and that should give us 9.3 volts. For V sub D, that should be equals to V sub K equals 2.7 volts. In this example, we are to identify the potential of this terminal here, so labeled as V sub naught. So here's the solution. Take note that this diagram here means that this terminal here is connected to a source that is equals to 10 volts, and that this is connected to ground. And this terminal here is also connected to a source, the negative of the source. This is 2 volts, and this is also connected to ground. So to determine whether the uh, diode is in forward or reverse biased, we can remove temporarily the diode. So let's remove that. So this is 1.2K, this is 4.7K, and this is V naught. So this is the plus, the minus, this is our VOC. So we can perform KVL there. So starting from here, so we have minus 10. There's no current because it is an open circuit. So current here is 0. So there is no drop across the resistances. So minus 10 plus 0 plus VOC plus 0 again, then minus 2 equals 0. So that should give us VOC equals to 12 volts. So that means that this diode here will be forward biased and therefore can be replaced by its turn-on voltage. So that will so this will give us a more simplified circuit that looks like this. And from here we can determine the current. So let's compute for this current. So we can write KVL. So starting here, that would be, or here, let's start here. So that would be minus 2, minus 10, plus zero point 0.7. So this voltage plus 1.2 plus 4.7, that should be 5.9K I equals to 0. And that should give us I equals 1.915 milliamps. Now to get V naught, Well, the voltage drop across the 4.7 would be, it is a plus here, it is a minus here. So we can get B naught equals to this potential here, which is minus 2. Remember, this is our uh, ground there. So this one is 2 volts. So to get here, that means that it should be 2. So this point here is has a higher potential than this point. So that means that we should add 4.7 K times I, and that should give us, um, so this is minus, so that should give us 7 volts. Okay, so this is our answer. This should be a negative 2 here.